Okay, so I'm going to record some short videos where I talk about some of these key papers about climate change. And I'm going to start by talking about integrated assessment models. And first up is Golosov et al. To give you an idea of one relatively cutting-edge model. So I skip the introduction and take you straight to their overview of the model, which starts at the bottom of page 46, the general model. I realize, by the way, you probably can't see this on the camera, but the idea is just so you can hopefully see where I am in the model. Okay, so what are the key elements of the model? Here's the first one. That we have a representative household with a utility function, which is the expectation at time 0 of the sum over infinite time or infinite periods of beta to the t u of ct. So what's this? This is what the representative household wants to maximize. It's just the sum, the expectation of the sum of discounted utility. And this is the discount factor, so this beta is less than 1, yeah? So beta to the naught is 1, beta to the power 1 is beta, then we have beta squared in time 2, period 2, beta cubed in period 3, beta is less than 1, so this is discounting utility. And a bit later on, we're going to find that the utility function is actually defined like this. That utility from consumption is just the log of consumption. So this is giving us diminishing returns to consumption, isn't it? This is U, this is C. When you double consumption, you don't double utility, okay? You have diminishing returns. So that's the utility function. Okay, next up we've got a resource constraint, which basically says, look, we've got this factory with capital KT in it, and it's producing YT. What happens to that? Some of it goes off to consumption, and some of it is returned to the factory or the representative factory to build up the capital stock. So how much is returned is YT minus CT, isn't it? So that adds to the capital stock. So what's KT plus 1? It's YT minus CT, that's the new capital, plus KT, the old capital. But the old capital, some of it depreciates. So that's how capital evolves in the economy. And then the next equation, that was the capital equation. The next one just says production in time t is some function which we call f naught at time t of capital, what's that n? I can't remember. That must be technology, energy inputs, and the stock of N is labor, yeah, of course it is. Capital, labor, energy, and this is the stock of greenhouse gases. So F naught is going to be an increasing function of these boys, but decreasing in S. Okay, so where does the energy come from? We saw where the capital comes from, foregone consumption. where does the energy come from? Well, it turns out they actually have three sources of energy, and it's basically oil, coal, and renewables. If I remember rightly, that's how they talk about them. And the coal, they say, look, there's so much coal, in any realistic scenario, we're not going to use it up. It's going to be left in the ground at some point, so therefore we treat coal as inexhaustible. On the other hand, the oil is going to run out at some point, or it may do, so we need an equation. We're on page 48 now. We need an equation showing how oil inputs lead to a reduction in the stock, and we can't use up more stock than we've got from the start. And of course renewables, they are renewables, so nothing like this applies for the renewables. Okay, and at this point I actually jumped forward to page 59 to see exactly how they define the energy produced from oil and coal. And it's basically the energy you can get out, which you then feed into the factory, is a function of the productivity times the labor you devote to the extraction. So it's a super simple, super intuitive energy production function for oil and coal. The more people you put into extraction, the more oil and coal you'll get out, and the more energy you'll get out. So they don't define that earlier to sort of try to keep it as general as they can at that point. Okay, I remember I got that slightly wrong. So they actually assume that oil is free to extract. There are no costs, because it's basically, they think, look, oil is so cheap to extract, we can treat it as zero. And this function actually applies to coal, which is more costly to extract, and renewables. So again, the more people you put into making solar panels and building dams and so on, the more renewable energy you'll get out. Okay, so having finished with the final good production sector and the energy sector and the capital, we then say, look, the resources can be allocated, and they will be allocated kind of optimally by the firms. So some of the labour will go to the production firms, some will go to the three different energy sectors, and the capital stock will also be distributed between the final good production firms and the energy sectors in order to make the markets clear. Okay. And then the last thing, I think, the sort of key thing in the model is, oh no, not the last thing. The stock of gas in the atmosphere, carbon dioxide in the atmosphere, if you like, or carbon dioxide equivalents, is a pretty straightforward linear function of the emissions in all the periods prior to the current period. Okay. So they're basically assuming a very simple function with, there is decay, but it's quite a nice simple decay function. So having set things up super general, they then start specifying things a little bit more. One thing they specify is the log utility, which I already mentioned. The next thing they specify is damages. So here they say, look, this is the general function, but then they say this is actually 1 minus a damage function times a new function, f bar or f tilde, I can't read it, it's too small. So they've now introduced a damage function, d of s, and this multiplies the productivity, the sort of baseline production. So the point is, if S is naught, and S is of course the additional stock of carbon dioxide in the atmosphere above the natural level. If S is naught, then you get baseline production. F bar. But as S rises, you start losing production because you've got this 1 minus D of S. Okay. So, what this means is that for a given level of S, you always lose a given percentage or proportion of your baseline. So whether you're rich or poor, there's some level of the stock that'll knock 1% off your production, the same level. So like China, India and the US will all be losing 1% of their production at a given level of the stock, for instance. And this is a really standard assumption in the literature. Furthermore, and to make things even simpler, page 51, they say, look, 1 minus D of S is e to the minus gamma S minus S bar, where S minus S bar is the natural level. So this is the excess stock. So, again, what does this mean? This is the pre-multiplier of baseline production, isn't it? So what is this pre-multiplier equal to? As a function of S minus S bar. So when S minus S bar is naught, i.e. S is at its natural level, we have e to the naught, which is 1. And then as S goes up, we have e to the minus gamma, that's a gamma, times something which is getting bigger and bigger. And e to the minus something, with the something here getting bigger, it's an exponential decay, isn't it? So remember, this is the pre-multiplier of production. So when the stock is at its natural level, production is at its baseline level. The more the stock, the atmospheric stock increases, the less production we end up with. This is quite a conservative damage function, yeah. You could imagine some other damage function might go like this. That if stock starts getting too big, production collapses to 0. This is like environmental total catastrophe. Even though production approaches 0 here, which is obviously catastrophic, it's still not as catastrophic in a way. This is kind of a conservative function. So, what do they do next? Of course, they set up the social planner's problem, which is to maximize expected utility for the household, the representative household, subject to all these constraints about how you produce, what happens to the stock, what happens to capital, etc. Okay, and then they take first order conditions. We're not going to go through those, okay, because they're a bit messy. We're going to jump straight to their proposition 1, which says, and actually we're not even going to bother with the equation. The point is that the marginal externality cost of emissions should be the same, okay, across all the sectors or whatever. Yeah, we're going to end up with a fixed marginal externality cost of emissions at each time. Okay, it'll vary over time. And then they do a little bit more simplification, but it's not unreasonable stuff. And then they basically say that this externality cost is a fixed proportion. It's proportional to the level of GDP. So the higher productivity, the higher you value the marginal damages. Okay, if you're twice as rich, your marginal damages double. So what do they do next? They go to what they call the decentralized equilibrium, in other words, the market solution. And because they've explicitly introduced the household problem, they need to think, okay, what does each representative individual do? So you have a maximization problem for them, which involves saving, choices about savings and stuff like that. In addition, you have the firm's profit maximization problem. And in this profit maximization problem, page 55, they introduce a per unit tax on the resource tau T. So what's the firm's problem? The energy firm's problem, is maximizing the quantity of energy times the price minus the tax hang on. Not quite sure what that Q is actually, because this is the price minus the tax times the quantity of energy minus the capital needed minus the labor needed. I'm not sure what that term is either, I'll have to think about that. Okay, I had a quick think. So this Q is a kind of a discount factor, and this is just the sum of input costs. And here we're still, at this point, we're still trying to keep it general and saying that the energy firm could be using input of capital, labor, or other energy sources. Actually, it turns out later we're just going to assume they only use labor. Okay. And, hey presto, we end up with the tax on carbon emissions should be the same for all firms, and it should be equal to the marginal damages caused by carbon emissions that we found in the planner's economy. So, summarizing, what do we get out of this? This is the tax. If we bring this y over, we can see that the tax at time t is equal to yt, so it's a linear function of GDP at that time. So if GDP is going to grow because of technological progress, then the tax rate will grow over time. Then it's times the damage factor, which will typically be constant, and then it's times this, which is a bunch of decay factors to do with the stock, and then this discount rate thing. And the smaller is beta, that's the bigger the discount rate. The smaller should be the tax. Let me just think about that. Yeah, of course, sorry. If beta is small, this bottom line, this stuff on the bottom line is big, which makes this whole thing small and makes the tax small. So the discount rate is super important here, and obviously the damage factor and the decay assumptions. So then when we parameterize, and what do they get? Well, they end up pretty much agreeing with Nordhaus that it's sort of 50 to 100 bucks or whatever it is per ton of carbon. But that's how they did it, that's the point. Okay, so that's given you an idea of how one IAM works. Now let's have a look at what Pindyck has to say about IAMs in general.